Good morning, everyone. My name is Kuan-Wei, and today I will be presenting CST, Character State Transformer, for Object-Conditioned Human Motion Prediction. This work is a collaboration between the Institute of Science Tokyo, the National Institute of Informatics, and Denso IT Laboratory. Human motion prediction is a critical challenge in applications such as gaming, animation, and robotics. Our goal is to generate realistic human motion in a frame-by-frame manner, considering how characters interact with objects in the environment, like walking toward and sitting on a chair. However, the main challenge of this task is limited data availability. High-quality mocap data is expensive and task-specific. To ensure real-time adaptability, we enhance autoregressive models. These models sequentially predict each frame, making them suitable for interactive applications, such as gaming. Compared to sequence-to-sequence models, autoregressive models are generally faster due to their lightweight architecture, and they provide more controllability during the prediction process. For example, in an autoregressive model, we can change the user input in the middle of the prediction by providing a different goal as input, which is very practical for game character motion generation. Specifically, our model is a transformer-based VAE that takes the current state vector and the interactive object as input and generates the next character state as output. It is common in this field for researchers to define a customized state vector. Now let's introduce its components. The state vector consists of a joint pose component where a 3D joint position, rotation, and velocity are defined. Additionally, there are temporal states that include trajectories, right directions, and continuous action labels from the past to the future. Besides that, there are also goal states that drive the character to move toward the goal. Since the state vector is customized, it also requires specialized data to train the model. Furthermore, high frame rate data is required for autoregressive models, which further limits the amount of training data. To overcome data scarcity, our solution introduces a transformer-based variational autoencoder, VAE, to handle variable length input sequences. We divide the state vector into task-specific components and task-agnostic components. The human joint state, which consists only of pose and velocity, is considered task-agnostic, and we designed a human joint transformer, HJT, encoder to process it. This encoder can be pre-trained on diverse datasets with different skeleton representations before fine-tuning for specific tasks. By leveraging existing motion datasets, we improve generalization while reducing reliance on task-specific data. On the other hand, the spatiotemporal state, which contains continuous action labels and goals, is considered task-specific. We designed a spatiotemporal state transformer, SST encoder, for feature extraction. Eventually, features from the object encoder, HJT, and SST are fused in the prediction head to generate the next character state. The figure on the right-hand side shows the pre-training scheme for HJT. We utilize mask recovery as the pre-training task. The joint information is randomly masked out and recovered by the mask recovery head. The pre-trained HJT is later fine-tuned with other components on a dataset containing human-object interactions. The first core component of CST is the Human Joint Transformer, HJT, designed to process skeletal structures efficiently. The model takes in joint positions, rotations, and velocities as input. Instead of fixed joint encodings, we introduce body part priors to improve generalization. This allows us to handle different numbers of joints. The transformer architecture utilizes attention mechanisms to learn spatial relationships across different body joints. Since HJT is task-agnostic, we can pre-train it using large-scale motion datasets before fine-tuning it for specific applications. The second key component is the spatiotemporal state transformer, SST, which models trajectory and goal interaction. Specifically, we adopt positional encoding, which maps spatial features into a high-dimensional space. Through layers of self-attention and cross-attention, we capture dependencies between current motion states and future goals, ensuring smooth transitions between actions. This enables effective spatial temporal learning, which is essential for scene-aware motion prediction. We evaluate CST against SAMP, a baseline model for autoregressive object-conditioned motion prediction. In addition, we compare results trained from scratch and pre-trained on two different motion capture datasets, Human Act 12 and CMU motion capture. All these models are trained on the SAMP dataset. We adopt three evaluation metrics, including the mean per joint position error, MPJPE, and mean per joint rotation error, MPJRE, for frame-level evaluation, as well as the Frechet distance for sequence-level evaluation. Here are the results. CST reduces model size from size 17 Evans to 12 men parameters, making it more efficient. Additionally, pre-trained CST outperforms SAMP by over 10%, especially in long-term motion prediction. Pre-training on CMU motion capture yields the best results, highlighting the advantage of leveraging large datasets. For the pre-training task, we use a masked skeleton reconstruction task. Similar to masked autoencoders, this technique helps HJT learn human motion dynamics without relying on specific task annotations. However, we observed that excessively high masking ratios can lead to overfitting to average poses. Now, let's look at some visualizations showcasing CST-generated motion alongside object interactions, e.g., a character sitting on a chair. Generally speaking, our model is able to generate diverse and natural motion. The penetration artifacts observed here are due to fitting issues that exist in the training data. Since improving the performance of data-driven approaches is our focus, we do not add additional physical regulations here. Next, we would like to show you how we generate the motion in the video. We present the 60-step pre-training result, which follows the same training conditions. Our motion prediction results are closer to the ground truth compared to SAMP. Although there are some artifacts, pose vibrations, in the training dataset, which are also learned by the model, especially models with strong capacity, the output pose can be smoothed if the velocity components are used. To recap, we introduced CST, a transformer-based framework for object-conditioned human motion prediction. There are three primary takeaways. 1. HJT and SST enable task-agnostic and task-specific learning, improving motion quality. 2. Pre-training on large-scale datasets enhances generalization and reduces model size. 3. CST achieves state-of-the-art results, outperforming existing methods while using fewer parameters. That concludes my presentation. Thank you for your time. For more details, please visit our project page.